The 2025 Nobel Prize in Physics was just awarded to John Clark, Michael H. Devoret, and John M. Martinez for their experimental work revealing that the weird world of quantum mechanics can be seen not just at the level of atoms and particles, but even at sizes that human beings are more familiar with. The heart of their discovery is one of the most fundamental and frankly weirdest features of quantum mechanics, something called quantum tunneling. If I throw this ball, or anything, against a wall, it bounces back. It's a lemon, it doesn't bounce very well every single time. But if we take this into the quantum realm, by shrinking this example down to the subatomic level, and instead of a ball imagine an electron, and make our wall very, very thin, with each bounce against the wall there is some small chance that the electron doesn't bounce back, but instead passes straight through the wall and appears on the other side without ever being present inside the wall. That, other than my favourite explanation as to how Santa gets down small chimneys, is the idea that shows us how weird the quantum world can be, and thinking about quantum objects as tiny billiard balls isn't accurate. Instead, we need to think about them as objects without any definite edges, as waves. In quantum mechanics, a particle doesn't have one exact position. Instead, it can be described by a wave function, a mathematical shape that tells you where it's most likely to be found. The taller the wave, the higher the chance that you'll detect it there. The wave fades at its edges, but it never quite reaches zero, meaning that there is always a small chance that that particle could be somewhere unexpected. So when that probability wave meets a barrier, part of it is reflected, but part of it can seep through, carrying the tiny possibility that that particle can appear on the other side as if by magic. That means that for an electron traveling down a wire, if there is a break in the wire, there is a small chance that that electron could hop over the gap and continue on its journey, as if the wire wasn't broken at all. In fact, we are engineering computer chips down to the sizes where that is becoming a real problem. Components are so close together, electrons can jump from one circuit to another, even when we don't really want them to. Weird, but that is the quantum worldview, and for most of the 20th century, quantum effects were believed to be limited to this tiny regime, exclusively to electrons, photons, atoms, and things small, since larger objects always appear to behave classically. But in the 1980s, at the University of California, Berkeley, John Clark, Michael Devoret, and John Martinez set out to find if these sorts of strange behaviors could also happen at the macro scale. They turned to this idea of the electron jumping across a gap, but in a specific form called a Josephson junction, where two superconducting wires are sandwiched either side of an insulating barrier which acts as the gap, creating an impenetrable wall that classical electrons shouldn't be able to cross. In a normal wire, as electrons are negatively charged, they repel each other as well as scatter off of other atoms, constantly losing momentum. That scattering is what causes electrical resistance and produces heat and light in our electronics. But in a superconductor, when cooled down to some of the lowest temperatures in the universe, everything changes. As an electron moves, it slightly distorts the lattice of metal ions around it, leaving behind a small region of positive charge. Another electron can feel that positive region and is attracted to it, following behind the first electron's path, and linking these two electrons together into something we call Cooper pairs. Inside the superconductor, billions of these pairs move together without any resistance at all, described by a single collective wave function. When that wave function reaches the thin insulating barrier of the Josephson junction, it can extend into the barrier, overlapping with the wave function on the other side. That overlap allows Cooper pairs to tunnel through, creating a steady supercurrent with zero voltage, the hallmark of superconductivity. This effect won Brian Josephson, the junction's name, the Nobel Prize back in 1973. The Berkeley team, though, wanted to take this one step further. They wanted to see if the whole wave function, representing billions of Cooper pairs within the wire, could tunnel through the barrier as a single quantum object. That would be macroscopic quantum tunneling, tunneling on a range that is relevant to human beings. To run the experiment, they needed to measure the tiniest possible changes in current and voltage across the junction. They used a dilution refrigerator to cool the junction to just a few tens of millikelvin, temperatures colder than interstellar space, and surrounded the setup with layers of magnetic shielding and microwave filtering. Then, as they passed a precisely controlled current through the junction, at low currents, everything behaved as superconductivity predicts. A steady-state supercurrent flowed, producing no voltage at all as Cooper pairs tunneled across the barrier. But as the current continued to increase, at a certain critical value, counterintuitively to superconducting systems, suddenly a voltage started to appear. That spike meant that the collective quantum state had escaped its confinement and was tunneling across the junction. Now, it turns out the macroscopic quantum tunneling of a wave function representing billions of electrons is kind of hard to draw, so if that doesn't mean much to you, I'm kind of right there with you. Without relying on just talking through the math, let's talk about why that voltage is arising and why that tells us this is a macroscopic quantum tunneling event. As the wave function escapes, its relative overlap compared to the wave function on the right-hand side changes. That continual variance is what's driving a voltage, and that's what tells us it's something about this macroscopic wave function that's actually moving, and it's different from individual Cooper pairs just tunneling over the junction. Maybe the more important question to ask here is, how do we actually know this is a quantum tunneling process that is happening? Because there are situations where classical physics can explain this switch. At higher temperatures, random thermal energy can jolt the wave function over the barrier, a process called thermal activation. Actually, at high temperatures, we see a strong correlation between temperature and the current required to see this phenomenon. What tells us though that this is a quantum process is that as these temperatures are decreased, the escape rate stops showing any dependence on temperature at all, moving it out of how classical systems behave. At these temperatures, this process can only be the quantum system representing billions of Cooper pairs tunneling through the barrier, proving to us for the very first time that quantum properties of the universe happen even at scales above the individual particle. Back in 1935, Schrödinger was talking about a cat in a box to make a point about how absurd quantum theory sounds when you take it out of the microscopic world. But here we are, thanks to Clark, Deveray and Martinez, we've seen actually it is entirely possible. It's not the zombie cap that we were promised, but it laid the foundations for superconducting qubits that we use today, where the same principles of these early Josephson junctions are harnessed to control quantum states. This discovery often gets so much visibility and celebration because it is the underpinning part of so much of what quantum mechanics and quantum computation now relies upon. But keep in mind that this is all the output of that discovery. This took decades to finally prove and was driven purely by curiosity and a need to know, without necessarily understanding any of what might be potentially unlocked, just testing a theory out against the behavior of the universe until we proved it one way or the other. And it's why this work feels so worthy of a Nobel Prize to me. If you've made it this far without your wave function collapsing and would like to support the channel and the content that we make, hit the like button and join our Patreon if you'd like. You'll see some updates about a quantum computing company that I just visited. Congratulations to the rest of this year's Nobel laureates. Thank you for watching. I'll see you in the next one.